with nothing, build it tall, dress it up, call it law. Pull the base, watch it fall, nothing holding it at all. If it cancels what remains, zero left behind the claim. Say it balances neat and clean, but that's not how the real world leans. Say it once, say it twice. Pretty words don't make it right. Break the base, cut the ties, watch the whole thing collapse tonight. Woo! Debunk the premise, expose the lies. Every result afterwards, null and void. Debunk the premise, expose the lies. Every result afterward, null and void. Hey, hey, null and void. Null and void. Null and void. Null and void. Null and void, null and void. Debunk the premise, expose the
Welcome to the podcast where we don't just debunk the minutia, we debunk the premise. How are you doing this evening, brother?
I'm pretty good. Everything that they do, all their science, everything that they make up, it's all null and void.
Absolutely. So this whole Artemis thing, you know, I would say most people have sort of done their last words on it. We're approaching this from a totally different angle. We're not going to go into the CGI and the AI footage and, you know, debate ISO settings and whether or not this is a photograph or whether or not it's CGI, that kind of stuff. We are going to take this to a premise that once you debunk the premise, the entire thing falls apart as a lie. So that is, can rockets travel in space? And what makes space special is that it's a vacuum. What do you have to say about this?
You know, so right off the top, if you actually look at the place that we live, where we're created, where we dwell, you actually discover and research where the, you know, edges of reality are, you start to see there's these very hard limits, right? So if you go too low in the ocean, you die, you get squished by the pressure of the water. If you go too high in the sky, right, the pressure still increases on you. Actually, it actually pulls outwards the expansion in the reciprocal way that you do when you're underwater. So, you know, once you figure out that you can only go so high and then you die, your oil, your eyes, your tongue, your blood just boils. You're done. You're done. You're not.
And we're not talking about as a result of temperature either. We're talking about pressure, right?
Yeah, the pressure due to the elevation, either above or below sea level, right? And when you actually look at it, you can't go too far down. You can't go too far up. All you got to really do is really examine humans themselves and the way they interact throughout the world and what's taking place here. And you start to understand, okay, well, if we can't get out of here, we're born in here, right? We're all born in here the same way, everybody that's here, human-wise and animal-wise. But we can't get out. There's no leaving. This place was created as an absolute fortress. And when you start to understand that it's a more of a virtual reality, so it's a higher level of understanding where you're in an avatar and you're living multiple lives here in this realm, then you find out, okay, well, we're not really ready to travel to other places in creation. I don't think we've proven ourselves as a species here in our evolution at this point. There's way too many lies. There's way too many deceptive people. There's way too many people that are doing things that are just not acceptable. And tonight we're going to be getting into how they're distorting things that we observe. So when I take a walk and I step on the ground and I push myself off my feet, I'm pushing off the ground. And the traction that I have between whatever is touching the ground and my body is what propels me forward. And this is the mechanics that we can test and repeat. Everybody that's ever moved an inch in this reality has experienced this.
But what you just said right there goes directly in the face of Newtonian physics. Don't you know the third law?
The third law, right? There's an opposite and equal reaction for every action. And I just think what they do, they say that the ground is propelling my foot or body or arm or anything that moves on it forward, right? So there's no actual force that's being exerted from my feet hitting the ground and pushing, or a skate, or anything that you're doing on the top of a surface, especially in a boat with a canoe and an oar. They just say that you just have to go like this with the oar and the boat shall just travel forward. They've completely, took something that's true and then flipped it upside down and handed it out. And they say, well, in space, our rocket doesn't need to push off air. We don't need to have air pressure because we believe in Newton's third law, so that when we ignite whatever we have that we burn, it just pushes the vehicle forward. And because there's no resistance from an atmosphere, they say that it'll just travel straight ahead without actually having anything to push off of.
Yeah. So what we're going to be doing tonight is we're going to be absolutely destroying Newton's third law. But the thing is we're not the first ones to do it. It's actually the debunks of it are all over the place. And it's just Swiss cheese. The whole law, this whole law of physics is really just an exception and may only work in a few instances. And we're going to be showing everybody. So once you can see through the magic trick, once you can see that, so in this third law, they're going to be applying an equal and opposite force to something. So this force is a made up force of whatever. They use the word force, like Star Wars uses the word force. When we talk about force, we're talking about physical force of actually pushing, pulling, lifting. These are physical forces. And then you have your non-physical forces, which are in the form of electromagnetic fields or just fields in general. And so a real force is the push-pull kinetic type. And then a field is energetic. It still has an effect on an object, depending on what it is, its composition, stuff like that. But it has a limited area that can affect it because all fields observe the inverse square law. So they fall off very quickly and lose their power. They're only localized. And there's so many, with the shills that we're going to be covering here, there's so many magical forces like, gravity and they come up with all these other different forces that are not real. And so now going back to that formula, if you add an equal and opposite thing to a formula, you've changed it by absolutely nothing, right? You did nothing. If it cancels out, if the formula cancels out the formula you proposed cancels out, it did absolutely nothing. So ask yourself, why would you even propose such a law that actually adds nothing? We're going to be showing you all where the magic tricks lie as far as how when they start doing their canceling process, they mentally get you to think, okay, well, this canceled, but that didn't cancel. And that's the reason it's now moving. Where before you have the law, like it is as it is, you apply this law, it makes no changes whatsoever. And then somehow they want you to believe that something's different. All right. So there is a magic trick involved. We want to dispel that lie. And once you can see through it, you're going to actually have more common sense physics in your mind. You're not going to be thinking that the earth is pushing you back as you're walking. all these different types of things while you're swimming, that the water is pushing you forward. No, these are all non-realities, but are being used ultimately to be able to explain how a rocket would move in a vacuum. And that's what it's all for. So we're going to bust that myth that rockets would work in a vacuum. We're going to actually use YouTube footage, stuff like this, where people have done different experiments in vacuum chambers, but we're going to break it down for real and show you which parts of it is the debunk of a rocket working in space. And, you know, some of this is just, there's different types of physics involved. We're going to be showing everybody how, as pressure goes down, a canister that has pressure would be going out and explode. We've talked about that before, but we've got a different angle that we're going to go through this evening regarding how rockets wouldn't work in space.
Well, it takes it to another level. So you start to understand what happens at the atmosphere when there is no pressure, when it gets down below zero, and you start to get into vacuum-like conditions. You have to check, what does this do to people, and hold that up to what we're being shown as the supposed proof of them being in that that environment. And the same thing goes with the propulsion system. If you have a vacuum and you can't ignite anything, well, then that just null and voids any observation that they try to show you, like with the graphics and different types of technologies and different types of magic tricks and movie setups that they can do with things to fool the eyes. It's when we actually test and verify something, that's what we actually hold as truth. And tonight, Jason, I'm sure you're going to lay out a good, solid foundation of evidence that's going to let everybody know exactly, you know, can rockets actually fly in space? You be the judge on the other side of the screen.
Yeah, well, the first thing that we have to do is we have to educate the audience in what the scientists are saying is taking place, because chances are you would have never, ever even conceived that this is what they say is taking place, right? You've never thought about it. And if you did think about it at all, this was not the answer that you were coming up with in your head. But we have to know what it is that they are saying is taking place. So let's go through this, Shill's video here. Rockets do work in the vacuum of space. And let's start hearing this guy's explanations for how this works, right? Go ahead and play.
And thanks for tuning in, everybody. Make sure to leave a comment below if you got any disagreeing topics.
First, let's start with Newton's third law of motion, which states for every action there's an equal and opposite reaction. And it's important to note forces always occur in pairs. That will be...
All right, so this is the Newton's third law. Right away, they jump straight into this. And it's not a law, right? For every action, there is an equal and opposite reaction. Forces always occur in pairs. This is a completely not true statement. For every action, there's an equal and opposite reaction. So I'm going to give you an example here. There is a fly flying around in the house, and I take a fly swatter, and I go over, and I swat the fly, and it's pancaked, and it's done. Where's the equal and opposite reaction? Right? The
fly smack, the fly smacker.
The fly's not coming back. It's gone. It's gone. It's no longer with us. So you can come up with an infinite amount of situations where an action doesn't have an equal and opposite reaction. Right? This is, you can literally spend the rest of eternity coming up with new scenarios where the action doesn't equal. Right? That's simple.
It's a gradient of results.
Yeah.
It's not, there's not a definitive, repetitive motion to it. And here they are. And again, everything that you see, so the scientists are like, oh no, we can't push off of the vacuum of outer space. What do we do? And then so some other guy sits there and thinks about it. Maybe it takes him a semester or a year or 2 years. And he's like, that's it. We'll just invent the opposite reaction of it, and we'll say they cancel each other out. And when space, we'll just remove this fake one here, and then it'll just make the vehicle travel forward.
Yeah, you're starting to give people the magic trick right there. So, and then force always occurring in pairs. Well, This is great if the entire universe is just 2 billiard balls. But what happens if there's 3? Right? How do you have it occur in pairs? If your cue ball hits 2 balls at the same time, it's not in pairs anymore. So, I mean, you can come up with an infinite amount of situations where it doesn't show up in pairs. Yeah. So it's just word salad gibberish.
Very important later. Now let's look at it in terms of balanced versus unbalanced forces. This rock has a mass of 1 kilogram. If we round off the acceleration caused by gravity, that's 10 meters per second squared. Multiply those together and we get 10 newtons. So that means I have to apply 10 newtons of force in the upward direction with my hand to keep it from moving. So with these forces balanced, the rock won't fall. If I applied more force, it would go up, but if I let go, it will drop. That was in slow.
All right, so let's look at multiple scenarios. You take that rock and you put it on a table. All right. You use the energy, you lift it up, whatever the weight is, you put it on top of the table. Now that weight is there on the table pressing down. It's been added to the mass of the table. You're not doing anything to hold it up anymore. And the table is not pushing the rock back up. But they're going to say that. Check this out.
Slow motion. Here it is at regular speed. So now the forces are unbalanced. So gravity wins. Now let's look at another situation involving forces.
So hold on.
And that's...
But let's just throw a quick red flag out there, like challenge, however they do it, in baseball now, that you get to challenge the umpire if he says that it's not a strike and it's a strike, or a ball, vice versa. So he says that because the rock falls, boom, therefore gravity. Well, again, I'm going to continue to repeat this every single time I'm in front of a microphone and a camera. So why has it that never has there been in the entire history of humanity anything pulled closer to something else due to its sheer size? Our cars aren't attracted to mountains. Flies don't get sucked into the side of a wall. Nothing pulls anything to it on its own weight itself, unless you like create some sort of a table where it's got like a sheet or something that's flexible. Then you can move something and it can sort of go like down into a spiral like that. And that's the actual mind trick that they try to show you guys. Like the gravity is an imaginary force that's actually made up through movement and then density of the different things in this reality.
Yeah, specific density. And mass does not attract mass.
A balloon. When you fill it with air, the air pushes off in all directions and they end up canceling each other out until you let air out.
They didn't cancel themselves out. They
Then
made
the
it to
force-
the end of the container.
It's just a container, and it's not. It's all trapped at the same time.
Canceled out by the elasticity of the balloon material itself.
Yeah, so in this situation where we have atmospheric pressure, right, 14.7 pounds at sea level, when you release it here, that pushes against the other air, and that's what sends it forward. Guess what happens when you release a balloon in a vacuum chamber? Well, you don't get the chance because we'll show you the balloon breaks because of the pressure that was holding the balloon together. Once that's gone, the balloon expands and breaks.
Forces become unbalanced. The air going out no longer has any effect on the balloon. It's the air forces on the other side that win. Let's look at it again in slow motion this time, and remember that forces always act in pairs. Now all the other forces in the balloon cancel out, but the one that pushes forward and the one that pushes it in reverse do matter, because as soon as I let go of the balloon, the air that would push it in reverse escapes, no longer having any pressure inside the balloon, and the force on the opposite side that pushes it forward wins.
So this is the core of the magic trick right here. They're saying that they were canceling each other out, but as soon as you let go here, and there's no resistance, then it's going to spring forward this way. So they're completely negating the fact that you have thrust coming out of a nozzle and pushing it forward. They're saying, no, 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 that air going out doesn't do anything. It's all of a sudden you can just exit out of the equation, and all we have is this arrow inside the balloon here pushing this direction now, right?
Yeah, well, the only way to actually verify this would be to rotate the balloon after you let go of it. And if it still travels in that direction with the thrust in the reciprocal direction, then yeah, you verified that it maintained its momentum in that direction. But I guarantee you, if there's atmosphere to push off of whatever direction that thrust is pointing, the balloon will go in the reciprocal direction.
Absolutely.
Now let's see how this applies to rockets. In the rocket,
You notice how all of the graphics for they say that a rocket scientist is supposed to be the greatest thing, right?
Yeah.
How come everything is made for preschool? I mean, this isn't middle school. This isn't high school type stuff. Everything's made for preschool.
you have the fuel and an oxidizer, and together they will make a chemical reaction. In the combustion chamber, you get an explosion, and forces push off in all directions.
An explosion or combustion? An explosion is not the same as combustion, and it says combustion chamber here. So our science teacher, he's going a little fanciful on us with the explosion talk.
And they cancel each other out, except there's a force pushing forward and a force that would push in reverse. But the force that would push in reverse leaves the rocket altogether and no longer has any effect. It can't cancel out the forward force.
Oh, because it went out the back and it can't stop the force that's in here going forward. See, this is the mind trick. They get people thinking that there's a force inside the combustion chamber that is getting things to move forward, and it has nothing to do with the stuff coming out the back, because in space there's supposed to be no air, a vacuum. Right?
The main takeaway is they're admitting that there's no ability to thrust. They're admitting it in their actual teaching.
Yeah,
right?
No medium to push off of.
But then they come up with their excuse, which is that they invent everything has two different sides. It's all dualistic now, and then we just remove this one now.
Mm-hmm.
When in actuality, you've done nothing except for taking away the atmosphere.
Yeah.
Emphasize this because I've seen even science YouTube channels and science programs on television talking about how rockets work, and whenever they say it pushes off the ground or it pushes off the air, that's wrong. That's
You get that? This guy's
wrong.
chastising all those science ignorant people, saying it pushes off of something.
not how it works. The fact that the exhaust gases are exiting through the nozzle means it's not pushing against anything. The exhaust pushes against nothing.
Nothing.
The reason why the rocket moves is because the forward force that could be canceled out by the reverse force isn't canceled out, so it wins. The forward force wins because there's nothing canceling it out. Here's a YouTube channel called Lab Rat that does a very good job explaining it. Check this out.
Now here's what the pressure profile looks like inside the rocket motor. First of all, we have combustion. And that creates pressure forces on the top of the casing, on the bottom of the casing, on the front, and the back of the casing. Now, the upward and downward forces don't contribute to the leftward force creating the thrust in this picture, so we can eliminate those.
Cancel.
And also, if you look at the right-hand side of the motor, there's a hole at the back end. Oh. Now, there's no surface for the pressure to act on, so there's no pressure force acting in the area of the throat of the nozzle. So if we eliminate balanced forces again,
all of a sudden, everything went away, and all we have is two arrows pointing this direction now.
Yeah, it's just magically being magnetically drawn that direction.
Nope.
See that we have a leftward force created by the pressure inside the casing. There's also a pressure inside the nozzle, exit cone, and this acts perpendicular to the surfaces. If we break those pressures up into components, eliminate the up and down forces that don't contribute
Cancel these
to
out.
the actual thrust of the rocket motor.
The
we
actual
see a pressure
thrust.
force on
Now you get all the arrows going this way.
He said the actual thrust. Actual thrust, the force that moves the object.
Because anything that went out here into a vacuum would have nothing to push off of, and there would be no thrust.
Sort of like, you know, trying to walk or drive anything with a smooth surface on ice. How far do you move?
Yeah, they're keeping the thrust inside the container. This is literally like trying to lift yourself up by the bootstraps. Right? How do you do
That's
that?
ridiculous.
on the exit cone of the nozzle. Now it's these leftward acting forces that are actually the thrust of the rocket motor.
Left.
No.
Imagine that these opposing forces are like a tug of war. The blue team is providing a forward force, and the red team is providing a reverse force. But what happens if the red team all lets go? They are no longer providing any force in this tug of war, and they are gone.
They're gone. So as soon as
What?
yeah, this everybody when you have a tug of war, right? This animation that's to explain how space travel works says that as soon as you let go, you take off flying.
They do. No, you do.
Yeah.
You do.
The
They let go.
So-
They gave up, and
they flew away.
How could they show this graphic, this supposed model, this whole entire demonstration? And you like you
Because-
said, when you think of someone that's smart, you always say, well, you don't have to be a rocket scientist. And when you actually study the rocket science tree, it's like grade 3 level, like they're eating crayons and stuff.
And we'll get to the point where they start trying to tell us that it's the Earth pushing these people. Oh,
On. Reverse force missing, the forward force wins. And that's what happens in a rocket engine because there's a nozzle.
So it's like a kid inventing a fake player in a game so that he can just win the game. Just the other player just forfeits because you invented it, right? That it's such a silly trick. When you actually look at this, I don't know how anybody can believe a single thing NASA says, or any supposed space travel.
yeah. Watch the red guys let go of the rope.
They are no longer providing any force in this tug of war, and they are gone. Reverse force
where'd they-
missing.
What
What did he
why
say?
did
What lost force missing?
they're not providing any force.
Longer providing any force in this tug of war, and they are gone. Reverse force
You just fly away.
Reverse force. I could use some of that reverse force to like something you don't want in your face.
missing,
That'd be
the
great.
forward force wins. And that's what happens in a rocket engine because there's a nozzle. Here's the
All right. So this is if you do any research on this topic, you're going to come across this footage, this vacuum chamber, this YouTube channel. So we're going to go into depth about this vacuum chamber in a little bit, but let's just go ahead and take a first look at this and what he shows.
rocket test in the vacuum chamber done by the Action Lab.
Hey, it worked. Look how cool that looks. You can see the stream of smoke particles shooting out of the rocket
You can also see that it absolutely did not move, right? It's been still. Now wait for this shock wave to come back.
like a laser beam. Since there's very little air in the chamber, there's nothing for the stream of gas to bump into.
But here's another huge issue. If it's a vacuum chamber, there's supposed to be no air in here, and he's showing this at a
It's got like
0.02
smoke rings.
ATM atmospheres, and we'll show the conversions for this where you'll help see what kind of vacuum this is. Like it took me a little bit to be able to compare different vacuums. It's just not terminology that most people are familiar with, and so this is an exceptionally weak vacuum right here, And then what's happening is gases are being expelled from this. And so the vacuum's gone, right? As soon as you emit more gases into this area, you've destroyed your vacuum. And so you're not actually testing for a vacuum situation anymore. It's important to keep in mind.
So it has a very straight flow with little turbulence. So if we were at this pressure in the sky, we wouldn't be able to use a traditional jet engine to provide thrust. We would have to use a rocket. Rockets not only work in a vacuum, but they actually work better in a vacuum than at atmospheric pressure. The propulsion in a rocket comes from the fact that you're expelling gas out the nozzle of the rocket at high speeds. In order to conserve momentum, that means that there has to be an equal and opposite.
Conserve momentum. This is part of the third law of physics, Newtonian physics. And this conservation of momentum is the idea that all equations have to balance out and that there's these pairs of equal and opposite forces, when the truth is it's completely random, right? The amount of energy that goes from a golf club into a golf ball and how far it travels and all that kind of stuff, there's not an equal amount of energy being reversed the other direction. It's all coming from the human body load, the spring that's in the shaft of the club head speed, and then the contact as far as how far that golf ball is going to travel. And no two swings are the same, and you'll never get the same results, right? But they want to have these balanced equations where they think that there's always an absolute equal going into every single reaction, counter reaction.
Opposite force on the rocket in the opposite direction. This is similar to how a strong hose pushes you backwards due to the water being forced out of the nozzle.
But there would be absolutely no force on the person if he was in an absolute vacuum. Right?
Yeah.
No force. So they're just showing you, okay, well, this is what happens in atmospheric pressure. But if you took that fire hose into outer space and sprayed it, it wouldn't have any force because it would just.
And it would freeze. The liquid would instantly be ice. It'd probably blow up
because of the lack of pressure.
Yeah.
This is happening with rockets, except that it's gases moving at ultrasonic speeds being shot out the nozzle.
Now we just know that someone watching this video is going to point out the fact that this smoke reached the wall. But how does that help the rocket? It doesn't. The gases, once it leaves the nozzle, is no longer part of the rocket at all. Hitting the wall makes no difference. It may apply a force over here.
Shows atmosphere. If there was no atmosphere, it would just go into a misty cloud. It wouldn't form a ring and pull against the side of the container. It's rippling through atmosphere.
Yeah, those shock waves with that air, you could actually see them bouncing back and blasting and moving this thing. It hasn't moved yet, just off of squirting the jet stream out.
It's crazy.
On the wall. But that doesn't translate back to the rocket at all.
Yeah, it does.
That's why we feel the need to keep repeating this so that people understand it. Even science
That's how you mind control
programs
somebody, by
on
repeating
YouTube
a
and
line.
on TV programs I've seen get this wrong. The push in the rocket is inside going forward. The gases leaving the nozzle aren't canceling it out. That's the important thing to remember.
So the only way I posit that would be true is if this was a balloon. And the balloon was towards the top of the rocket. Then yes, you would be floating up if it was filled with some kind of either hot air or helium, right? True. But if you have something that provides thrust, creating a force that you can bolt to something and then take a measuring device and say, wow, that's 10,000 pounds of thrust out of that rocket engine. The energy is not in the top of the rocket. We just measured the thrust power of the actual rocket. Then you can have any kind of battery or any type of fluid or liquid that you want to try to use to make the thrust. Then we talk about what makes more thrust and what makes less thrust. So, steam would be an amazing thing to actually use for rocketry and other things like that too. We're not even going to get into that right now, but the thrust is being created where you don't take the rocket off and then measure the upwards ascension of the rocket, you actually have to measure the thrust power in the rocket itself on a dyno. Jason, would you imagine? Don't we see them on History Channel where they fire up that thing and it creates all the smoke clouds and then it rains, that demonstration that they show? That's the engine bolted to something and them firing it up, right? Doing a test fire.
Yeah, when they test these engines, they can see how many pounds of thrust that they generate. The funny thing is they measure it out here where the gases is being expelled. The pressure is not picking this thing up from the inside that combustion chamber. They want you to believe that if there was no Earth here and this was just in outer space, that it would still be going forward, even in a vacuum, because these gases are being released at the bottom right here. And it's trying to pick yourself up by the bootstrap and nonsensical. So once you can start seeing that the thrust is actually in the back here and it's combustion, we have burning gases. It can be solid fuel, it can be liquid fuels being combined. We have something burning. There's flame here, and that's important because once we get into the no pressure situation, all of a sudden we lose flame. So they say, well, it carries its own oxidizer. Well, we're going to be showing you that that's still a serious, serious problem.
It's just like the tug of war I showed earlier. The team that let go of the rope is the hot gases leaving the nozzle. They're not applying a force to the rocket at all anymore. They may be applying a force to the ground below the rocket, but that doesn't do the rocket any good. It's the force inside the rocket that's not canceled out. The tug of war team that won the battle. So the question we
Absolute gibberish.
Absolute gibberish. Let's hear one of their big high priests of science talk about how space is a vacuum quick.
Where we presume there to be no space, there can be no nothing.
Profound.
I keep hearing the
Has to be
phrase,
something.
the vacuum of space. How exactly is it a vacuum?
Right. Okay.
Good
So
question.
when I was a kid, a vacuum was a physical object.
Yes, it was.
When I heard physicists speak of the vacuum of space, I just imagine all these hoovers,
Right.
in the sky.
Right.
So I didn't know that a vacuum was a thing. It was a concept, and then you make a machine that duplicates that thing. I just didn't know that till I learned. Okay. So a vacuum is where there's basically no air. Okay. You can have
Okay, no air. So this is interesting. When we're talking about vacuums, we say, it's got a hard, strong vacuum. And so we think of a pump working hard to pump the air out of a container. And we call that a vacuum. And then space is said to be a vacuum. But what Neil just let slide right there is that it's no air. There's no air. So there's no pressure. Right. So what you're trying to achieve with a vacuum is to get to no air, which here on Earth, it requires a lot of super vacuum strength, right? In a strong container. And you're always going to hit a limit. You just can't vacuum out all the air perfectly.
objects there, but when we think of a vacuum, it's not a place where there isn't anything. It's a place where there's no air molecules moving, typically. All right. Generally, you can have some, and we would still classify it as a vacuum. Because you have to distinguish like a regular old vacuum or a perfect vacuum.
Right.
Now, you know what happens if there's an object and you take away all the air molecules? The object outgasses.
Oh.
There are air molecules embedded in
Inside?
the surface of that object, and they start coming out. It's fascinating. Then you heat it, it sends out more. Just
All right, so we're going to get to these plexiglass vacuum chambers, and one of the problems that you have is as you draw down the vacuum, you literally suck gas out of the acrylic chamber itself, out of the material.
very hard to make a perfect vacuum. Very hard. So, here's an old saying. Nature abhors a vacuum. These are people who've never been into space. Most of the universe is
So nobody's been to space, and nature abhors a vacuum. It's so incredibly difficult to create because we exist in this 14.7 pound pounds per square inch pressure, right? We actually exist in a lot of pressure.
This is a vacuum. Nature loves a vacuum.
Nice.
Was I Trumpy in there?
No.
Love
Nature loves a vacuum.
a vacuum. So
Perfect. Preferably Trump vacuums.
Trump.
Trump.
Yeah, they just going into Trump.
Why? Why do they got to start impersonating Trump? Just talk about the
Right.
vacuum.
So let's go ahead and start digging into, this is the guy that has the
Giant vacuum chamber. They
giant vacuum chamber. So if we take a step back here and look at it, you can see that it's got nice thick acrylic walls to it. And this is probably as high quality, see-through and large quantity, large volume vacuum chamber you're going to come across. Right? The only thing is that every single one of these acrylic, you can see through them type vacuum chambers, they have a very weak limit. And so you're never ever achieving a real vacuum with any container that you can actually see through. Right? So if you want a strong vacuum, you're going to have to go with a solid metal container, and you're definitely not going to do a box like this. It's going to be a sphere or a cylinder.
Well,
and
everything, not one single unwelded plate. You weld the door on.
yeah, and then if you want to, then you put your camera inside of this device.
But then it'll destroy the camera.
But the moment you have this clear see-through box like this, you already know that this is home hobbyist type stuff, and it's not serious. So let's go ahead and jump through this a little bit. He shows us this so they use very specialty type materials. This is a chemically coated type paper that
You might have guessed that wasn't real money. But what it actually was made of is nitrocellulose, or flash paper. So flash paper like this is made by mixing nitric acid with cellulose, and it makes this extremely flammable paper. Magicians frequently use this because it can go up in flames and there's no residue left over. You don't see any ashes, and it goes up really fast.
Literal magic.
Really
trick,
bright
right?
too.
They're trying
Literal.
to prove the vacuum of space so that rockets can move, and they started off by showing you a magic trick.
All right, so here's what he's got his vacuum chamber set to, this minus 845 millibar, and I'll show you a chart that this is a weak vacuum. It doesn't even compare to something like the vacuum that an HVAC system has. You know, your home heating, cooling system, how it's got a vacuum in the system. This doesn't even compare to the vacuum that's in your home heating system.
Well, and another thing to point out is that a lot of this stuff that they show you on these videos is deceptive, right? They're skewing things. They're actually letting pressure in. They're crop zooming. They're selecting and choosing certain areas to show you, and they're specifically editing and hiding out other areas.
All right, so he's got his magic paper in his acrylic vacuum box. Let's see what he comes up with.
A laser. So I need some black pigment that will absorb the light a little bit better and it'll get hot enough. So let's shine our laser on it. Look at that, it still burns. There's no visible flame, though it just kind of disappears into a gas. That's so cool.
All this gas that you're seeing in here is all evidence that we don't have a vacuum in this container anymore.
What's cool with this big of a volume is that the pressure in the chamber actually doesn't change by any measurable amount after it burns. This is because the
Lies.
volume of the gas released is so small compared to the volume of the total chamber. So you can see we're still at low pressure, negative 827 millibar,
Which isn't a strong vacuum. Let me go ahead and start showing you all. So we've got millibars and we've got PSI, pounds per square inch. And so sea level, we got our 14.7 pounds per square inch, which is the 1013 millibar. This is the numbers that you hear associated with hurricanes, right? And so then at each 10,000 feet, we've got this drop in pressure where you can see this 14.7 is already very low at 1.74 at 50,000 feet. So right here at the 120 millibar range, this is what the very best, like those acrylic boxes, like we're watching that video right now. So the equivalent of what he's able to achieve is the air pressure at 50,000 feet. So most commercial airplanes, all that kind of stuff, they stay in the 40,000 foot range because they're getting into the range where we have as strong of a vacuum as that vacuum chamber, the acrylic one, is showing us. And they have to keep air pressure in order for you to not die right away, because as this air pressure gets lower and lower, right in this range is where your blood will start to boil, just because of the lack of pressure, because water boils at body temperature at this elevation. So this is not, this right here is the equivalent to being at about 50,000 feet.
Which is relative to my atmospheric pressure, which is 846 millibar. So the total pressure in the chamber is only around 0.02 atmospheres, which is the same pressure we started with before we burned the paper. This is good because it means we won't increase the pressure in the vacuum chamber from the rocket gases alone. Okay, now that we know it'll ignite in a vacuum, let's make our rocket. To do this, I need something transparent that I can shine my laser through. So let's use a syringe. I'm just gonna.
So this is the guy that makes this setup that we saw in the last video. And we see that when it ignites, that it shoots out across here. While it wasn't changing the position until we have the shock wave of the air coming back again.
Hey, it worked. Look how cool that looks. You can see the stream of smoke particles shooting out of the rocket like a laser beam.
It didn't move until the air came and pushed it on the rebound.
Whoops.
Since there's very little air in the chamber, there's nothing for the stream of gas to bump into, so it has a very straight flow with little turbulence. So if we were at this pressure in the sky, we wouldn't be able to use a traditional jet engine to provide thrust.
Well, you can't use a traditional jet engine.
No, yeah, he admits it. You can't do it. Doesn't work.
Yeah. So here's part of the whole vacuum thing. So you've got a regular balloon that's blown up a normal size, and then as you decrease the pressure in here, you see that the balloon begins to get larger and larger and larger until it breaks its tensile strength and it bursts. So this is the fate of all high altitude balloons, that if they're not controlled and if they're just allowed to go up and up and up and up, they will all self-terminate by the fact that there's not enough pressure around the outside of it. They hit their tensile strength and they burst. And so this would be the absolute exact same thing that would happen in the Artemis capsule, the pressurized part of the spacecraft. As it went up in altitude, you would see the entire capsule swell out and out and out until it ruptured outwards.
And they don't even have any cross braces or anything linking the two sides of the top to the bottom. The engineering is just all wrong. It would completely be exploded. It would be gone.
So here's a guy
Give us undeniable results.
that's made a plexiglass vacuum chamber that he wants to show everybody how rockets in a vacuum chamber work. Newton's third law of motion visualized. So as we go through this, we're going to learn just how difficult it is to get a solid fuel. This is what everybody says. You got to have a solid fuel, where you got to have your fuel and oxidizer. And since the solid fuel has both of those, that this is what they would use in outer space where there's no pressure, right? Because no oxygen, no fire. They say you got to bring your own. And so he's using those types of engines, and he's Let's get him putting it all together. He's getting ready to test it.
Way. You gotta be kidding me. So apparently I have some findings from this first phase of the experiment, and that is, I just realized that the vacuum has now created an environment where it becomes more difficult to ignite the solid rocket booster. This means that there is some...
What?
So you're telling me it won't fly? It won't burn?
Yeah, well, listen to what he says here. This means that there is some truth to what the conspiracy theorists think.
Truth to what the conspiracy theorists think. It's more difficult to ignite a solid rocket booster in a vacuum because we tried this in atmospheric pressure, ignited just fine. And I mean, that's definitely, that's definitely an interesting finding. I have just one more problem. Due to the rapid depressurization of the chamber after that last attempt, one of the seams was compromised.
Oh, no.
Yeah, so you've got an environment where you've got all this vacuum, right? And then you repressurize. So all these seams are subject to failure each and every time.
To re-weld that seam and put a couple of supports in where the deflection occurred. That demonstration just gives you an example of how much force pulling a vacuum in a chamber like this has. So it's essentially at sea level 14.7 psi, which is 14.7 pounds for every square inch pushing in on each side of this chamber. So if you do the math, which I already did, it's about 80,000 pounds combined. So you got...
You got that?
80,000 pounds combined.
Yeah, so this is not that far off from the amount of pressure that's actually on the human body. If we quickly take a look at...
That's what he's saying. It's at sea level.
Yeah, so the average surface area of an adult human body is approximately 2,800 to 3,000 square inches. And then at sea level, the 14.7 pounds per square inch means that the average human has about 46,000 pounds of pressure being exhibited across their entire body. You gotta think about this for a second. That sounds like a lot. So we're in the same situation as like the fish are. Fish can swim around in the water and it doesn't feel the pressure on its body because it's made of water and things that the pressure doesn't affect it. So we're 90% water in the body and you can't compress the water anymore. So our bodies can handle this 46,000 pounds of pressure at sea level. The problem is if we don't have the pressure, actually, if we go up and we lose that pressure, not only do we get heavier, but now all of a sudden our body wants to expand and burst outwards. Go back to
20,000 pounds on each one of these walls trying to cave this thing in. Since that last attempt was a failure, I invited the AIAA team over for the rest of the experiment because I know how much they love hang fires and they have a lot more experience with this propellant than I do in case I run into more issues along the way. So pretty much all that smoke that came out was the igniter, nothing else. And I think they're in for a big surprise because I don't think it's going to be that easy to ignite in a full vacuum. But we'll see. All right, I'll hit it now. We're good.
Strong.
3, 2, 1.
Yeah, so this is just the vacuum pump that you would use in an AC system here. You have this, it's a pretty thick acrylic, but very, very little bracing. If you actually pulled a hard vacuum in this, what would happen? The whole thing would implode. Absolutely.
1.
Oh.
Oh! There you go.
There you go.
That
No
is
fire.
the problem that we're having all along. What do you think, Mike?
We can repack an igniter and try it again.
Looks like we may need some atmospheric pressure in the actual boost.
What? We may need some atmospheric pressure in order to start the the combustion of this is a solid fuel, right? You just admit it. We may need the atmospheric pressure
to get it to ignite. Once it's ignited, I think it's going to do okay. What do you think, Mike?
We'll try it again. It could be from the lack of air, from the type of igniter, from the cap being on it. Hard to say.
So you think once it's lit in a vacuum, it's going to stay lit?
It should, yeah. It's got its own oxidizer.
Let's see what it looks like.
Did you see
not a
how
very thick lid.
Yeah, look at that.
It's only a half inch. I was trying to say that to you earlier. The top
It
of
should,
this
yeah. It's got its own
vacuum chamber
oxidizer.
Let's see what it looks like.
Whoa.
Maybe 3/16.
So if they had any real vacuum in here, this entire thing would just buckle in like nobody's business. Right? A person inside here inhaling would almost be enough to break this plexiglass.
Wow. But it still stopped it from working.
It looks like, I mean, the igniter kind of ignited, right?
Yeah, it definitely did.
Yeah, look at that. Kind of ignited, but I don't know. It doesn't look like it fully ignited. This is going to be our second attempt. We got another igniter in place, and what do we do differently this time?
He's not showing any gauges.
Completely new motor. This was the old one that we just test fired.
Yeah, I don't think the motor's a problem, though. I think it's the vacuum.
We'll try. We'll see what happens. That's a brand new motor, brand new igniters. We doubled them up this time.
Cool.
All right,
Feeling good.
Let's do it.
He's confident.
All right.
Let's go.
3, 2, 1, go. Go, go. Oh! No! It failed.
It failed. Conspiracy theorists were right again.
Again.
Go. Go, go. Oh! No! It failed.
Oh. Put it to music.
So they've got to come up with a new plan, and the plan that they come up with is to seal the engine. So what's happening is, without it sealed, as the vacuum is being drawn down, the air is being pulled out of these solid fuel rocket engines. So what they're going to do here is they're going to seal the rocket engines so that the air pressure is trapped inside there, and then
atmospheric pressure inside of that rocket motor until ignition occurs. And the idea is this thing's going to pop out, and the motor's going to light, ignite, and burn normally. That's the key word, burn normally.
that flexible top there. So they don't show what vacuum that they're going to. And here you could absolutely see that it let all the vacuum out, right? As soon as that went on,
right away,
all the vacuum's out of here. And so this is no longer a vacuum test, anybody. This is just a rocket motor pushing against the scale. And yes, it has thrust, but it's not in a vacuum.
Pop the back of the box.
Yeah, it's not in a vacuum. They get it to ignite because they have trapped air pressure in their solid fuel thing.
Pressure instantly on the gauge.
And yeah, it's right here. As you see all this smoke and stuff coming back here, watch these wood chips. This force is because of the thrust that's hitting the back of the chamber here. Watch the super slow-mo. You see how the wind? This isn't like a real vacuum chamber test. It's at open atmosphere pressure. All right, so that was their big win. And then they do it again with
These conditions is produced off of the pure reaction of the fuel burning and not from the thrust pushing against air or an atmosphere. Now, something that I found really interesting was where the main ignition occurred. If you look closely at the high-speed footage, you can see the majority of the gas started to ignite in the vacuum chamber, not right behind the rocket motor, as I would expect. I'm not sure why that is, but that looked pretty cool. Regardless of the gauge readings for our vacuum chamber,
he's got one more
the
experiment.
vacuum was obviously sufficient because this was our fourth attempt. We had to modify the rocket motor in order to get it to ignite.
So he's saying that the vacuum was sufficient because we had to modify the motor in order to get it to start. Right? None of this is well documented. If it was a real experiment and these were real results, we would want to see the actual pressure gauges recorded live, sitting in the corner here, multiple camera angles, everything showing the proof that there was no pressure failure in the canister, and you know, knowing exactly what vacuum was held. Right?
We didn't see any of that.
None of that. So he tries this next setup
In the vacuum chamber. That being said, I'm just gonna do one more experiment. I'm gonna get a really small model rocket motor, 1/10 the size of this solid rocket booster, and put it in the same chamber. And what that's gonna do is that's gonna essentially increase the amount of volume of our chamber by 10, since the motor is 1/10 the size of this motor. That burns a little bit slower than the solid rocket booster here. We're going to be able to see whether or not it's creating thrust in a vacuum, and that's going to further validate Newton's third law.
So, you know, he's demanding that. He's not, you know, suggesting that the results will go one way or the other. He's saying this is what we're going to show you, right, before the actual experiment.
All right, here it goes.
See, notice this time, this doesn't move at all. Doesn't move at all. Watch. There's a little bit of wiggling right here.
Okay, so that was another successful burn. The model rocket motor burned just fine in the vacuum chamber. Unfortunately, it didn't go exactly as planned because the sled got wedged in between the walls of the chamber.
So why wouldn't you do it again and show it moving? Right? No, he just shows and says, got wedged. That's the reason why it didn't move. So bad. So let's go ahead. We'll take a break here. And then when we come back, we're going to get into some fun clips that now that you're getting your feet wet in the whole vacuum pressure conversation, these next ones should really help you out. We'll be right back after this.
Desire.
And we are back, and we are going to check out, is fire possible in a vacuum? We got Cody's lab here, and he's going to show us some different products, and he's going to try to show us fire in a vacuum. So let's start checking this out.
When heated, the potassium nitrate gives off oxygen, which the sulfur and charcoal uses to burn. So I've got a little bit sitting in there. Let's apply the laser goggles, and let's light it off. First in the atmosphere, and then in the vacuum.
That burned.
Great. Yeah, wow.
Okay,
Not in
as you can
science
see, it
class.
produced lots of smoke and burned rather quickly.
The right color.
Most of the air is now gone. Let's see what happens.
Most of the air. Uh-oh.
Whoa.
Whoops.
The gunpowder did not ignite. I saw some smoke coming off of it, so I know it burned a little. Let's try again more in the center of the pile.
Let's try again. I don't get... Oh.
This is gunpowder, everyone.
Didn't work. Shucks.
And that's it. The gunpowder does not burn. I mean, it burns when the laser's on it, but other than that, no. It doesn't change from one particle to the next. That's interesting. So what I think is happening here is that the hot gas is produced from the burning gunpowder. Normally, as it expands, it encounters other gunpowder particles, heating them up and causing the chain reaction to occur. But in the vacuum, the gases expand so rapidly that they're not able to heat up the nearby gunpowder particles, and so the flame or the fire does not happen. Also, some of you know that when burning gunpowder in open air, it just sort of burns with a bright flame and lots of smoke. But when you put the gunpowder inside of a confined area, say a barrel of a gun, it explodes. It's because the confining...
Well, this works at regular air pressure. This absolutely works. But what he's showing is if this was in outer space, you wouldn't be able to light it.
Again, they don't show the other example. If you use this as evidence, you have to show it working, like you said, Jason, inside of a vacuum.
Yeah, because it wouldn't light, and you wouldn't get the fast combustion.
Pressure accelerates the combustion. Yeah, this is definitely, it didn't burn very much at all. Kind of hard to tell whether or not the individual grains burned up completely or not. So let's try something a bit more solid. Scott Manley actually messaged me and asked if I could try rocket fuel in this test, and so I'm going to be burning some rocket candy. This is a mixture of sugar, potassium nitrate, and iron oxide. This is used in amateur rockets because the ingredients are readily available and the amount of thrust it produces is quite high. So let's light this on fire and see how it does. So this is in Earth atmosphere.
It burns.
As you can see, it burns rather rapidly, producing a little bit of thrust even. As you can see towards the end, it moved it around. So now let's try it inside of a vacuum.
Oh, no.
Nothing.
It's like burning it, but not
No
igniting
ignition.
it.
No ignition.
That's interesting.
Interesting.
I did see some little poofs as it tried to burn, but it was unable to sustain itself. So even when it's in one solid piece, it can't chain and continue burning. So I've let a little bit more air back into the chamber. Let's see if it'll burn now.
Not showing us any numbers, not documenting any of it. Just
He's getting a little smoke by putting the atmosphere back.
That's a no-go on burn.
Still smoke.
Wait. It's kind of smoldering. And it's out. Acetone peroxide in the atmosphere in 3, 2, 1.
That worked.
Easy.
Yes, that's a little bit more volatile than gunpowder is.
Wow.
Acetone peroxide in vacuum in 3, 2, 1.
One. Oh.
No chain reaction.
It still didn't burn.
He laughs.
I'm actually disappointed. It needs something to confine it in order to get it to burn and then eventually explode. And at atmospheric pressure, the atmosphere
Needs
does
air.
it, but in the vacuum, there's
Doesn't
nothing
need
there.
something.
So far, nothing I've tried has been successful, but I was thinking about it, and everything I've tried up to this point has produced gases as a product of its combustion. So I thought, what if I tried something that didn't produce gases? How about some thermite? This is a mixture of iron oxide and aluminum. Well, normally this is actually magnesium powder because I didn't have any aluminum on hand. But the idea here is that the reaction will not produce gases. It might make a little bit, but primarily the product of the reaction is going to be molten iron. And molten iron, of course, you know, it's not a gas, so it's not going to leave as quickly, so maybe it can help chain the reaction along. So let's test this out. This is a thermite reaction in Earth's atmosphere.
And he
There we
doesn't
go.
show us the
Thermite.
vacuum level
Burned
either.
up.
Yeah.
I can see that there's little bits of iron, some magnesium
burned.
oxide floating
Yeah.
around. A little bit of smoke, but again, that's probably just from contaminants that burned up. So there we go. Let's try it in the vacuum.
That's a negative.
It's not burning.
I
Thermite.
did not get an ignition.
He's so dejected.
I see pieces flying all over the place, but none are actually igniting. I'm going to try again with the thermite, but this time I'm going to bake out any volatiles
Oh,
from
it's
the
gonna
iron
bake
oxide
it.
first.
That'll work.
That way, perhaps the laser won't push the pile around quite so much. Had a
Let's just-
binder with it. It might help us. if
Didn't
you're
work.
Using.
So Cody's lab just showed us how even these solid rocket fuels, right? The things that have their fuel and oxidizer built right into it, he can't get it to ignite in even a weak vacuum.
Oh,
This
no.
isn't, it's not even a strong vacuum. All right. Let's go ahead.
It's crazy.
And so here's another way to look at it. This isn't a chemical reaction, but this will still start to help you understand what can work in a vacuum chamber and what can't.
Chamber, do you think the drone would still be able to fly? Let's check. Okay, and what I'm gonna do is I'm gonna turn on the vacuum pump and then I'm going to fly it as I pump out the air, and let's see if it goes down as the air is getting pumped out. Okay, drone in a vacuum chamber. 3, 2, 1. Okay, I'm just gonna let it hover there. About negative 0.5 atmospheres.
It's going down.
I'm having to throttle up more and more and more. Negative 0.8 atmospheres. Look,
Uh-oh.
it's full throttle. It can't even get off the ground
Oh
now.
no.
I can't do anything.
So you're only going to be able to go so high in your drone.
Yeah, so there is a physical limit to how high you can go with any sort of propeller driven thing, be it a drone, be it a helicopter. It turns out that really the world record for the highest a helicopter has gone is to the top of Mount Everest. And that was with a specialty built helicopter for power and extreme lightweight. And it was extremely dangerous because at 30,000 feet, there's not enough air pressure for these propeller blades to maintain lift.
Yeah, so they just go down, until they get enough air pressure again to lift back off of.
Yeah.
Okay, so you can see the propeller spin. It's essentially just vibrating on the ground right now.
Can't fly.
And what's cool is look how long those blades spin after I turn it off.
What are you going to do?
Turn it off. Just barely stop because there's
Believe
no
in
air
a fantasy? So you can't ignite anything in a rocket. Can't use anything like a propeller to get through it. There's no way that you can get through these zones. You just can't.
Yeah.
They're created that way.
Fly.
So the housefly doesn't have lungs. So this is not an inhumane test. They can actually survive in a vacuum for a certain amount of time because they don't have lungs. So he pumps the air out of here and shows what happens to an ordinary housefly.
I have a little magnet in here where I can go get them and try to make them fly. Okay, can flies fly in a vacuum chamber? 3, 2, 1. Okay, we're at 0.8 atmospheres. They're still flying.
They can fly.
0.6 atmospheres. Still flying. Half an atmosphere. They're having a harder time flying. They keep landing, falling onto the ground. Okay, we're at 0.4 atmospheres.
They're not flying no more.
They keep falling to the ground. Yep, they can't fly. There's one more up here. So we're at 0.2 atmospheres.
It's cool they can cling to the side still.
Pause it right there. 0.2
That's
atmospheres.
crazy on the ceiling.
See how they just fall to the ground? There's one right here.
They can climb still. That's
So this isn't
really
even
interesting.
a full vacuum.
Not a full
Let me get it down
vacuum.
a little more.
pretty smart.
They can't fly.
They can't fly.
Okay, we're only at
And they already
0.1
know too.
atmospheres, not full
They already have
vacuum, but
adapted to
they
crawling.
They definitely can't fly. That's so weird. The flies have
That's
now
not weird.
become
That's
wasps. That's so weird.
What else we got? We got this is an anti-third law, Newtonian law of physics. In the Newtonian thing, you've got these equal and opposite reactions, and in it you would not be able to push a sailboat with a fan on the sailboat, but Mythbusters debunks the third law.
Forward, or it doesn't move at all.
Or, and it's a very real possibility, the shallow bottom boat with its top heavy sail goes bottom up.
Okay, we're in.
We have no idea what can go wrong. I mean, the mast could blow off, the boat could flip over, they might get sucked into the fan and chopped up into little pieces. Hey, good sailing. Good luck.
Was that about being sucked into the fan?
Chopped into little pieces?
They're off. Tori and the support vehicle tows them out to open water. With plenty of space, no major winds or currents, it's the perfect location for a spot of scientific sailing.
All right, you ready to do this?
Ready.
Okay, here we go. This is blow your own sail with the full-size boat.
It is moving.
I gotta tell you, the funniest part about this whole experiment is when we first turned on that fan and the boat just started to spin and dip down in one direction. Grant and I both were super wide-eyed because we thought we were going over.
They're wildly out of control. There's no forward movement, just a whole lot of spinning and crashing.
Take them out.
So when we first started and I gunned it, we
Check out of there.
started turning in a circle. And I was like, this is it. That's it.
Yeah, it is.
We're going on the water. But I turned it down and we tried it again. And actually what I found was, it's moving forward. You keep vectoring the fan.
He's walking
keep that
it.
thrust at the sail.
Right.
You can actually get it to go forward.
Well, it's walking. One side, one side, one side, one side, one.
And you have to stay on it.
Just
You can't
walking.
just set it and forget it. You have to keep working it. But eventually, you do get to go forward.
Wow. Debunk Newton's third law.
So they just debunked Newton's third law. Yeah. They did it. They did it. They even admit it.
Full day.
And no sail. But that's not the point. The myth asks, can you power a sailboat with your own fan? And you can.
Now, I don't know exactly what's going on because apparently we're flying in the face of Newton's laws. But here's what I think.
Oh, flying in the face of Newton's laws.
Way to go. Thank you guys so much for being such brave, journeyers into the unknown.
Mythbusters just debunked Isaac Newton's third law. The one that they use to say that rockets can work in a vacuum, right? I got a couple more examples to show you. Here's a guy
You be
that
the judge.
You be the judge.
I want you to see what he's got here.
What's going on?
Just
okay. Some tube.
Look at-
I've seen that stuff before.
what this is.
This baby, this looks great.
It's very expensive. You use that in labs, in forensics buildings. All the human remains get vacuumed through it.
They do a good job of trying to hide the end.
It's very expensive for these, by the way. Very
You can
expensive.
you can see right here that this is like a 1/4 inch.
Yeah,
1/4
it's
inch
glass.
of material.
It's glass.
Plexiglass.
Might be real glass.
Plastic.
Maybe this one, but they make them
This
glass.
is my idea to
Yeah.
mount this rocket engine inside the tube. And what this is gonna do, I got this idea from the inside of a scroll compressor. And what this is gonna do is not only hold our rocket in the center of the tube, it's also gonna allow us to see how much force the rocket is producing. I like the fact that it's kind of like a scale. It looks pretty sinister.
All right. So because of what we've watched already, we already know that he's not going to take this to a full vacuum because it's going to light. We've already seen how the rocket motors won't light in a vacuum.
All right, that looks just about good there. That looks
1/4 inch plexiglass with fittings
Nice.
like this. And you're gonna get a vacuum with this foam gasket here.
What is
And
that?
of
Some
course-
electrical tape?
Yeah,
Or not even? Duct tape.
not even.
We got our cameras all set up. Our chamber is in a vacuum. And we are ready to roll it. Godspeed. Model rocket engine in a
Why
vacuum.
does he laugh?
So we already know it wasn't in a vacuum
Full of
because of the
pressure.
fact because it lit, right? No vacuum. No vacuum in here whatsoever. And it doesn't move forward until the thrust bounces off the back end and then it starts pushing this forward.
Yep.
So this is junk science. Not a vacuum. See, it doesn't move until the thrust builds up, and then it starts to move. And it's not doing this in a vacuum. Not happening. So this is what they have to say about. So far, we've been looking at the solid rocket fuels a lot. And for like Artemis and stuff like this, they say that they use the fuel, the oxidizer, but liquid. Let's go ahead and see what they have to say about this.
The rocket consists of 2 tanks. One is oxidizer tank and another one is fuel tank. The fuel and oxidizer are separately stored in these 2 tanks. They are in the form of liquid. The combination of the fuel and oxidizer are called propellant. In liquid propellant rockets, the fuel and oxidizer are in the form of liquids, so these rockets are called liquid propellant rockets.
Come on.
Pumps for pumping oxidizer and fuel to the combustion chamber.
They say rocket science is the biggest science that there is. And here you've got a model that you've got 1, 2, 3, 4, 5 different parts.
Pretty basic.
And that's it. Pretty basic.
Combustion chamber. The fuel and oxidizer mixture are burning inside the combustion chamber.
Barrel or basket.
Here's the high tech, the
Fuel injector.
fuel injectors.
It convert liquid fuel and oxidizer mixture into small droplets and spray
Sprays.
inside the combustion chamber.
So we got to talk about this liquid fuel. So they say liquid hydrogen, liquid oxygen, and those things. So I have it right here. The temperatures at which you go to here. So simple comparison, the temperature needed for hydrogen to become a liquid is minus 423 degrees Fahrenheit, and for oxygen minus 297, and that is at sea level pressure. Now what happens is if you go up in altitude and the pressure decreases, the point at which these things boil, the boiling point goes down. And so all of a sudden, if you don't maintain these temperatures in lower pressure, it boils, it flash boils. It just goes straight from a liquid to a vapor, and it expands by like 1800% or something ridiculous. So it would absolutely burst and explode. All right. So there's where the rocket science gets real tricky is that the fact that you have to keep this at like minus 400 degrees, and it has to remain a liquid. And as you go up in altitude and the pressure decreases, all of a sudden it has a boiling point where it, as a liquid, will start to boil. And if it does that, it's going to explode.
Tank itself is a combustion chamber.
Mm-hmm.
Igniter. With the help of electrical signal, it generates spark and burn the propellant.
And so here's another thing that you can do is you can look at the YouTube videos of like Tesla coils in a vacuum chamber, and you'll see that a Tesla coil that has the sparks all flaring out or whatever, as you bring the vacuum down, there's no more spark. The spark doesn't shoot out through the air anymore because you're pumping out the air, right? So the spark doesn't travel through the air anymore. So this doesn't help. So you've got gas particles that are supposed to be liquid hydrogen, liquid oxygen that are supposed to come together. It's supposed to be injected out here. But the moment it goes into a chamber that's open out the back, it's going to expand and just shoot out the back without the igniter ever igniting it. We've went through the video before showing how these, you don't get the ignition, you don't get the burn. We showed it with the solid fuel. I haven't seen any examples of them doing it with the liquid fuel combination. I would like to see them do that in a vacuum as well. But this is another debunk, this electric shocker thing. If it's like a Tesla coil and it's normally going to be sparking out like this, once the air is gone, nope, not going to happen anymore. And I want to show people, this is the only like real footage that has all the data that we like to actually see. And so it's about to take off right here. And I want to have you listen to when the rocket actually burns out. We're going to check out what altitude that happens at.
Launch detected. Booster burnout.
So the booster is already burned out. We're at 16,000 feet.
20,000 feet. 30,000 feet.
Getting quiet.
35,000.
Do you hear that noise? Now all of a sudden we had another engine come on. Listen.
Sustainer ignition. 40,000.
So around the 36,000 range, all of a sudden we had a second engine go.
50,000 feet. Sustainer
burnout. So by 65,000 feet, the engine's burned out. And the reason why? Because we no longer have enough air pressure at this altitude to have combustion. Right?
burnout.
So the rest of this trip, it makes it up to 293,000 feet. The rest of this trip, the engines have already burned out. It's only working off of momentum now. It's momentum, and there's very little air pressure here, very little resistance. So it's going to go up, it's going to hit its peak altitude, and then start floating back down to Earth. There's never been an object launched, people, that didn't, once it burns out, it comes right back down. The metal doesn't float. It doesn't get to a point where it's just going to become weightless.
To the moon.
Float around, go to the moon.
Back again without anything to push off of.
No, this is the life of a rocket engine. And that is if you get into an altitude above 60,000 feet, you've got no more combustion. No more combustion. That's where the high altitude balloons, kick the butt of rocketry, because they get up into a 200,000 foot range before they burst. And this will make it, but it's just going to be an up and down trip. So this right here, this chart shows the different pressures at different altitudes. This is our pounds per square inch right here. And once again, so below sea level would be the highest pressure, but starting at sea level 14.7, our typical airplanes between 30 and 35,000 feet, and the top of Mount Everest, right? We're down to 4.3 pounds. So this is a third of what the air is on the ground. But then it doesn't take long. Our highest altitude, like the U-2 spy plane, makes it into the 60,000 foot range. There's only 1 pound per square inch of air at this level. And then it really tails off, where when we get to the 150, 200, 250,000 foot range, there's no air. This is where we see no combustion, right? And Newton's third law of like it's being pulled or pushed internally, right? As mass is being ejected out, the back end of it is just straight dumb. Everybody, use your brain. What parts of this has stood out to you, brother, that you think is some of the worst damning stuff that the rockets in space has to deal with?
Yeah, the pressure. The pressure is a huge thing. Once there's a vacuum is created, nothing burns and nothing pushes off anything. So those two things, it debunks any space travel idea above 250,000 feet of any drone or anything that you might build. And what they're doing is they're inventing something so that they can say that that's not real. The thing that they invent justifies something that they make not real, make you believe is real. So it's a basic, just a bit of a magic trick that they pull, a mind trick, where they just trick you into thinking, oh, well, there's always this equal and opposite thing. So now we'll just take one side of this away and then therefore we can just fly forward, while showing that it actually flies against the physical observations.
Yeah, so here you go, everybody. The Armstrong limit is a measure of altitude, right, where atmospheric pressure is sufficiently low that water boils at normal temperature of the human body. Exposure to pressure below this limit results in a rapid loss of consciousness, followed by a series of changes to cardiovascular, neurological systems. You have about 60 to 90 seconds. Your blood, your saliva, all the fluids in you begin to boil and turn to gases. That's really severe. Really, really severe. Like Ron talked about earlier, these are the constraints. These are the things that hold us. When they try to drill 8 miles deep, because the pressure gets more the deeper you go, the pressure ends up making the drill bits and all that just turn to molten metal. They can't keep it cool because the pressure is so extreme. And then on the upside, when the pressure becomes too low, right, if you're exposed to it at all, your liquids are going to boil at body temperature. Not only do rockets not work in a vacuum, so they wouldn't fly in space, they can't burn, on top of they don't push. Now you're saying that once you go to a certain height, your body just boils. Your eyes and tongue and throat and lungs just boil and you die. So there's no way that the Artemis crew, which would have absolutely gone through these conditions, right, while they were traveling, there's no way that that capsule was anything near what they're saying. There weren't enough structural cross braces, things like that, to hold it from the building just ripping itself to pieces, right? Just under this immense amount of vacuum force that they say exists. So those are my key takeaways. Yeah, this whole Newton's third law, we could spend an entire podcast just showing the nonsense of this. The first law, they say every object preserves its state of rest or uniform motion in a right line unless it's compelled to change that state by forces impressed thereon. Second law, the change of motion of an object is proportional to the force impressed and is made in the direction of the straight line in which the force is impressed. These are grade school type observations. And
this one goes off the rails.
The third one, to every action, there's always an opposed and equal reaction, or the mutual action of two bodies upon each other are always equal and directed to contrary parts.
And right there, look, they used the picture of a rocket taking off as supposed evidence for the third law.
Yeah, that's what it was made for. And it's so not true, this third law, and so made up. And it's because you're adding equal and opposite forces. It's a cancellation. It's a non-factor. It's not real. Right? So anything that's built off of the concept of rockets working in space, it's debunked. It's right from the premise. The entire concept does not work. And so we don't have to spend our time debunking all the CGI and the green screen and the wire harnesses and the vomit comet and the...
It goes on.
No, because rockets don't work in space.
Just that simple.
All right. Was there anything else that you wanted to highlight from this content, or?
No, just you be the judge. You do the tests. You at home. There's no one stopping you from building it or buying a vacuum chamber and doing tests of your own. Just be careful, and you'll find the results yourself. Just be smart when you do anything.
All right. Well, what's the next content people should be ready for, brother?
Probably Sunday night. We should be doing an update for Passover that's coming next week. And we'll do a little bit of a study into some of the parabolic scriptural stuff dealing with Passover, and it'll be exciting.
All right. Well, where's the only place people are going to get this content?
Only on the Hawashai News Networks.
You came into my life with all your pretty things. Put your helmet on and check the ignitions. Spaceship is out of sight. Earth is miles away. Now we're floating into space. Time never forgets. It counts the mouths with cigarettes. Just for one day, dolphins can call our names. We'll meet again, rebels on the dancing floor. We'll never dance alone.